So first, we're just going to play around with graphing by hand, and then we'll see how to do it on different graphing utilities. And again, most graphing utilities were designed to rectangular because that's the most common kind of coordinate system we use to graph. And so some graphing utilities don't do a great job with polars. They have their pros and their cons. So super simple things to graph in polar r equals 3. So if I count my concentric circles as 1, 2, 3, this is the third ring out. So r equals 3 would just be this circle right here. So I mentioned that earlier, circles centered at the pole, which is another name for the origin, super simple equation. And again, kind of like with x and y, if I say x equals 3, that means y can be anything and I get a vertical line. So if I say r equals 3 and I don't mention theta, that means r has to be 3, but theta can be any angle, right? That's why we get a circle. What if instead I said something like theta equals pi over 3? Now here I'm fixing theta, but r could be anything. So let's think about that. So what if r was 1? So pi over 3 would be this line here. R equals 1 is that first circle. That would be that point. If r was 2, that would be that point. If r is 3, it would be that point. 4, 5, 6, but r could be negative. So if I follow that line at pi over 3, then, ooh, that's pi over 6. I lied. Okay, let's make this pi over 6 then, since I already graphed a bunch of points. Pi over 6. If I had r equals -1, that would put me here. R equals -2, and so on. But r doesn't have to be a whole number. It could be a fraction, like a half or 1.5. So what I get then is this line right here would be theta equals pi over 6. And so I didn't mention r. What I get is just a line passing through the origin. So if you fix the radius and don't mention the angle, you get a circle centered at the origin at the pole. If you fix the angle but not the radius can be anything, and you get a line passing through the pole, through the origin. So some lines are super simple in polar. Circle center at the radius are super simple. Now in rectangular, something like y equals x would be a super simple thing. Let's take a look at what would r equals theta look like. Oops. Seems like that should be pretty simple. Now, when we usually write r as a function of theta, however, when we state points, we state theta first and r second, which is a little bit backwards with the way we do things with x and y. So I'm going to think about r theta. I'm going to make a table. Theta is the independent variable, right? That goes first in my tables. Independent variable, and then r is my dependent variable. So I'm just going to pick some angles for theta and see what happens. So this just says, bottom line, r has to be theta. So if I set theta to 0, well, r has to be 0 because r equals theta. If I set theta equal to pi over 6, then r has to be pi over 6. If I set theta equal to, say, pi over 4, then r would have to be pi over 4. If I set theta equal to pi over 3, then r would have to be pi over 3. Now, pi is pretty close to 3. So pi over 3 is pretty close to 1. So if r was equal to 1, theta would have to be 1. Now, since pi is really a little bigger than 3, then pi over 3 is a little bigger than 1. Just something to keep in mind. Now, to plot these, the thetas, those are pretty easy. I have these lines heading out. Like this line right here is pi over 6. Pi over 4 would be this one right here. Pi over 3 would be this one over here. Pi over 2 would be up here. Pi over 3 is a little bigger than 1, so an angle of 1 radian would be about right there. And so if I trace that 1 down to the 1 circle, that means I would have a point about right here. So super easy to point, relatively easy to plot points are 0, 0 is super easy, right? That's the pole. 1, 1 would be this point right here. I'm going to need a calculator to get some decimal values for the radius on this side. So although it's easy to grab those angles in this polar grid, I got to get some decimal values to get those radiuses, radii. So let's get a calculator. I had one here, so I need a decimal for pi over 6. I need a decimal for pi over 4. I need a decimal for pi over 3. All right, so 0.5-ish, 0.8-ish, 1-ish, a little bigger than 1. So 0.5, 0.8, 1. Let's graph that. I think I might have to zoom in on that here, kind of tight into the origin here. So let's see, pi over 6 was about 0.5, so that would be around here. Yeah, we better zoom in on that. And let's go over to this one right here. So let's say this is, let's go 1, 2, 3, the fourth circle. Let's that be 1 right there. So the second circle would be 0.5. So let's just kind of blow that up a little bit. All right, so I got the point 0, 0. I've got the point pi over 6 goes with about 0.5. So pi over 6.5, that's going to be about right there. Pi over 4 is going to be about, I'm just going to go with 0.8 because it's hard to graph more decimals than that. So this is 0.75, 0.8, so just a little farther. Pi over 4 is this one right here. So that should be around right there-ish. And pi over 3 is just a little bigger than 1. So here's 1. Pi over 3 is which line? This line here is my pi over 3. And I can see inside here, right? Pi over 6 here, pi over 3 there. And I want to be just a hair bigger than 1, so about right there. And so that's about 1.05-ish, 1, 1. Let's think about pi over 2. Pi over 2 is what as a decimal? 3.14, half of that would be what? 1.6 something, 0.68-ish maybe. Pi over 2, 1.57, I was a little off there. 1.6-ish, 1.6, this was about my first guess. So 1.6, so there's 1. 2 is out here, 1.5 would be right that circle. So trace that around till I get vertical is right here. So that's pi over 2. And what did I say? That's about 1.6. So that's 1.5 is this circle, 1.6 is going to be around there. And if I start connecting these dots here, what I'm going to see is they are spiraling outward. And think about it, r gets bigger as theta gets bigger. So at pi, which is out here, pi is about 3. This is 2 right there. 1, 2, 3, 4. That's 1. So 3 is going to be about out here-ish. So that spiral is going to end up out here, 3.14. So this is my best version of that spiral. And it's just going to keep going around because 2 pi is going to be way off my screen there. Now, what I want to do is I just want to see that spiral, but instead of me plotting the points, I'm going to make a computer do it. And Desmos can do this. You got to force it to in a weird way. And Geogebra can do this. And I think Geogebra is a little easier, but that's to be determined. So let's go over to, so I had this, I have a couple pages here that are going to help. So there's the polar coordinates in Geogebra and Desmos here. And I made this app to make some graphs for us. I'll show you how to use that one. And I got a slightly different one here. And then I got a Desmos version here. So I'm going to use Geogebra first. And I'm going to go over to this polar example. So I'm going to get it into a full screen by just clicking polar example. I'll also put this in the chat and the video if you don't happen to be on that page right now. So there in the chat is a link to, or there in the video in the comments or the description is a link to this right here. And I can, the tools are highlighted right now. So if I just click that, they'll slide out of the way. And I gave you a couple of notes on how to work with Geogebra. So polar point coordinates must be separated by a semicolon. So for this to be a polar point, and I can see it's on the radius 4 here, and then I can see that angle looks to be, this is about pi over 6 here, that's pi over 3. So that should be the point 4 pi over 3. This one over here, that's on radius 3, and that angle should be 2 pi over 3. And if I go to the algebra panel, it'll show me what I did here. So in the algebra panel, you can see I just typed 4 semicolon pi over 3. Now to get a graph, that's a bit trickier. I had to use their curve function, and I have a note about that here. So polar functions like r equals 4 cosine theta can be graphed using the curve function, and the notation is a bit tricky. And then I'll also show how to do this in Desmos, but it's not too bad. Now I made another app to help with this. And so the other app's slightly easier to use, but I'm just going to show this one. So I'm going to try to use the curve function. I'm going to add another curve down here. And to use the curve function, I just start typing curve, and it says, what do you want? And the first one is the one we want. Expression, parameter, start, end. And we're just going to use a slightly simpler version of that, but I'm going to click there to start. So my first expression has to be a polar point with my function r semicolon theta. Right, so that's what I show right here. Here's my r as a function without using the letter r, and then theta. So I'm just going to start typing over that, parentheses. Instead of r, I'm going to type my expression. Now my expression for r was just theta, and I can just start typing theta. Oh, no, I lied. I thought I could. Maybe I have to get theta from the tools here. Yep. ABC, Greek, theta. Oops. And then it messes that up. So we're just going to back up. Curve, try that again. Curve, see if we can type it right this time, parentheses, and then I need another parentheses, whatever your equation for r is. Mine was just r equals theta, so I'm just going to grab the theta. Semicolon, just theta no matter what. And then outside of the parentheses, so that's my first expression. My next expression is just theta on its own. And then after that, I want to tell it where to start theta and where to end theta. So I'm just going to start theta at, say, 0, and I'm going to go out to, say, pi. And that should graph what I was trying to graph on my paper earlier. And then I can keep going if I want. Suppose I want to go farther than pi, I could go out to 2 pi. 2 pi. And so it'll take that spiral out a bit farther there. Let's turn off the screen curve. So there's a graph, a partial graph of r equals theta. Okay, so that's using Geogebra. I made a simpler version of Geogebra. So that was kind of mainly to get started with points and how I use Geogebra to make curves. I have this sample polar graph in Geogebra. I'm gonna check that one out next. And then I'll share this link in the chat and the video. There's another one there. And this one I built a little bit different. So I'm just going to scroll down here. I put a box here for you to type your function. And in this version, I couldn't get theta to work, so I'm using a t instead of a theta. So notice it says polar function, polar r of t. So we're using t as the variable instead of theta. And then here I have a slider for theta, but it's called a, but that's okay. And if you click that, if you take it down to 0, it'll take it down to the beginning of this graph. And then as you move it out, it'll trace it along kind of point by point. So this is a really funky looking graph there. And then notice it just starts drawing over itself after that. All right, so if I go back here, so polar functions tend to be periodic, but not all of them are. But this one is, all of a sudden it redraws after I get to a certain point. And finding their periods is often a little tricky. All right, so all I have to do here is go to that little box and then delete whatever's there and replace it with whatever I want, like r equals theta would just be r equals t here. And then hit enter. Oops. I guess you didn't even have to hit enter. And I can then trace it out here. So if I go back to 0 for A, which is also T, I can trace that out. And then it goes off the screen, unfortunately. Let's see, there should be a zoom here. Ooh, well, that was search, not zoom. Ah, back. Zoom must be down here. We don't have the zoom on this window. All right. Maybe you'll find a different link to this that has a zoom. Remember that line we calculated earlier? That was 1 divided by parentheses. Let's see. When I was talking about lines in rectangular versus lines in polar, sine minus 2 cosine in the denominator. So that should just be a straight line if I graph it here. So sine of t is the variable here, and I started a parentheses for the denominator, minus 2 cosine of t, and then close the parentheses. And okay, there it is. So once I click on t, it starts calculating that, and the trace here is super weird. Notice that point I'm tracing bouncing around there. So that's a whole nother thing. I don't want to go over that right now. But you can see it is a straight line. And if you think about it, that is the line y equals 2x plus 1. But it's a bit more complicated in polar. All right, so that's 2 different tools I set up for graphing in Geogebra. Let's take a look at Desmos next. So Desmos, here's a picture of a graph. And if I click on it, it'll take me over to the, I already had Desmos open. So where is that one? Over here, maybe? Nope. This one? Thought I had it open. Interesting. Why did they give me that message? Oh, Geogebra up here is giving me the message. Yes, I want to leave that. Thank you. All right. So this takes me here. Now, this one, in my opinion, looks a little messier. In some cases, it's easier to use. So it's set up for you to enter your function up here. And then there's some strangeness down below that makes all of this happen. So ignore all the stuff below, but don't delete it, right? So r equals 1, r equals 2, those are all those circles there. And these spokes coming out there, those are the y equals tangent, y equals tangent, y equals tangent. Because remember, tangent tells us slope. So if I do y equals tangent of an angle times x, that's really y equals slope times x. So we're basically forcing Desmos to look like polar. And then I can just go replace this function with whatever I want up here. So aside from the stuff below, sometimes this way is easier to go. So if I just type r equals theta, and here I can actually type theta, and you can see that spiral coming out there in red. If I were to do r equals 1 over the sine of, and I can type theta, or I can get theta from the tools down here, minus 2 cosine of theta, then you should see that straight line that we got before. So here's a Desmos tool for graphing. So you get a couple options here for playing with graphs. They're both useful in their own ways. Let's see, what else did I want to show you? If you just wanted to plot points in Desmos, that's a little trickier. So let's look at that quick, and then we'll move on. Desmos really just doesn't do polar coordinates. You have to go out of your way to force it to do so. So to do a point, you actually have to enter the point as x is our cosine t and y is our sine t. Because it only knows how to plot x and y values. It doesn't, like Desmos, have a feature for plotting on its own polar values. So if I wanted to plot the point like I had before, 3 pi over 4, I would have to plot it by going x is our cosine theta, so 3 times the cosine of pi over 4, and then comma the y value, y equals our sine theta, so that would be 3 times the sine of pi over 4. And that's really the only way to graph polar points in Desmos. And if you want to plot a polar function in Desmos, then that's a lot more work. My recommendation is just use Where did it go? This one? This one, there we go. The one my friend set up here, where you can just type in your R up above, and it put those spokes in there for you.